This is a demonstration of using the Marine Magnetics Bob and BAM software for processing magnetometer data that originated from the AUV. A new survey would be created that looks like this. The data, once imported, would be on the left, and the map view of the data would be on the right. As you can see, there's some approach lines and maybe surfacing lines, plus approximately 50 survey lines completed by the AUV. On the left, we can zoom out to the whole survey by using the timescale slider. Simply right-click on it and select whole survey, and you can see the entire magnetic field data. The default vertical scale doesn't always match the specific survey. You can set it to whatever you like. In this case, 1000 seems to be an appropriate value because some of the anomalies encountered during the survey were very large. As you can see, moving the cursor along the survey path on the left also moves it to the corresponding position on the map. Before any processing can be done, this survey must be split into individual survey lines. Previously, you would have to do it manually using a tool such as this and giving it a name. But because there's such a large number of lines, there's a better tool for it that does this automatically for you. The tool that's found at the bottom of the toolbar. Simply draw a rectangle over the area that you want to subdivide into lines. Make sure you do not include any of the turns. A dialog will pop up asking if you'd like to give it a prefix for every line. So this is useful for multiple survey blocks being combined. In this case, there's only one survey block, so we'll just leave it blank. The Bob automatically subdivides the entire survey path into 53 survey lines. Now, some of them are tie lines or intersections created by approach and departure lines. And then there's a short segment here, number 51, that needs to be deleted. The list of the survey lines will appear in the panel here on the right of the profile. So all we need to do is find lines 51, 52, and 53, select them, and delete them. So now we have 50 lines. There's a checkbox near the top that can show you the entire survey path or only the path that's within the lines. The next step usually is to review each of the lines, looking for any segments of bad data that result from maybe coming too close to the bottom or excessively strong magnetic anomalies. This is done by simply clicking on the name of the line and then reviewing its profile quickly, looking for any abrupt drops, such as this one. Bob allows you to zoom in on a particular stretch of data by using a combination of the Alt key and the mouse. So zoom in. This looks like an instantaneous drop of several hundred nanotesla. This is probably an error in data. So you can simply select it using the Alt and mouse and then hit the delete key, and that stretch of the data would be deleted. Next line. You can see some of these anomalies are fairly large, but they are smooth. What we're looking for are abrupt shifts. There's one potentially here. In order to know for sure, just have to zoom in on it to take a better look. That looks like just a single point of data that's substantially lower than the rest. It will mess up the resulting map, so we should delete it. Next line. This stretch of data right here is obviously bad readings. We zoom in on it and change the vertical scale. You'll see that it's just a single point again that drops almost to 0. So I'm just going to select that one point and delete it. Change the vertical scale back to 1000 where we were and check the rest of the lines. During the survey, there were approximately 2 points collected for every second of survey. So deleting an occasional bad reading that occurs once on every 10th line out of 50 lines is not going to reduce the volume of data that's available for the mapping. So starting from here, to here, it looks like bad data. This is potentially an anomaly that was so abrupt and so large that the magnetometer didn't get a chance to measure it properly. Maybe the altitude at that particular point of the survey was just too close to the bottom. Okay, that's it. Now we have bad readings deleted and survey lines marked. So we're essentially ready for making a magnetic map out of this data. So we want to use only the data from the selected lines. And the one most important parameter we need to enter here is the line spacing, so that Bob can determine the resolution of the map. If you're not sure what the line spacing is, it's very easy to measure it from the map. Simply zoom in on a stretch of data, clearly showing the lines, and then use the measuring tool to measure the average line spacing. So this looks like approximately 4.5 meters, approximately 4 meters per line. So now we can go back here. There's 4 meters. Again, select only the lines that we wish to use. Make sure you select the total field tab first and enable the shading because it improves the data quality. We don't yet have any base station correction available to us because there's no base station data adapted to the survey. That is our magnetic field map. There are a couple of issues here to be processed and resolved, but this is a good preliminary view. What it shows immediately is that there's pronounced corrugation, as in like every other line is higher in reading, redder on the color scale than every other line. And that means that there's potentially a heading error. The cause of the heading error usually is the vehicle that's towing the magnetometer being too close to the magnetometer. So in this case, it's 5 meters away from the magnetometer, and the vehicle is equipped with some additional sensors that are more magnetic than typical light configuration of the vehicle. So that is the cause of this heading error, most likely. And it could have been eliminated by towing at a longer cable length, but it can easily be corrected in post-processing. The way to correct it is to rebuild the map, but enter a line bias shift for every line, and Bob will subtract or add the necessary correction so that this can be fixed. In order to know what value to use, I'm going to zoom in on a stretch of data that shows regular corrugation. So imagine this being ridges and troughs, ridges and troughs. What we need to do is find out what is the difference in magnetic field value between the ridges and the troughs, and then divide it by half to determine the amount of heading correction. That's relatively easy to do. Simply click on a point and look at the value that appears here in the total field. 46,313. And then on the next ridge, it's 46,315. And then in the middle, it's 46,305. So the difference between them is approximately 10 between here and here. So we just divide that by 2, and that's going to be our starting point, which we can later refine. So our lines are going north-south, so the line bearing 0 is okay. Anything within plus minus 30 degrees of that bearing would be considered the same line. And line bias is the value that Bob will add. So we will start from 5 and adjust as needed. Just add the new map. This is significantly better than before, but it's not fixed. So we can generate one more map and increase that line bias to the next available value, which is 6. Once again, better than before, but not quite fixed. So we can go ahead and increase this all the way to 7. Make one more map. This is a trial and error process. Normally, a number of corrections must be applied. One of them is layback correction, the other one is base station correction, and the third one is heading bias correction. So all those three are usually working in combination to mess up the data, and you have to figure them out one at a time. So that was our original map, and this is the map with a heading bias of 7. If we go past it to 8, we might end up overcorrecting and introducing an opposite heading shift, but it's worth a try. So that was 7, this was 8. It looks like it's just getting a little bit more corrugated again. This was 6, 7, 8. It appears that 7 is the best value. So what we can do is delete the unwanted grids here and keep only the one that we fixed. I'm going to also keep the original one just so we have a point of reference. Now you can see this ridge here. It only affects one line, and most likely it's a result of background change, or perhaps maybe an altitude change in the survey. So the next correction to apply is the base station correction. It's found in the survey menu. You import the base station from a file. This is what happened to the background magnetic field as the survey was taking place, and it's quite possible that these 3 high spikes occur exactly where we see the pronounced ridge on the map. So we can double check that by applying this correction and then regenerating the total field map. So let's build one more map, and this time we will check the box that says base station correction and keep heading bias value at 7. That is a significant improvement over this, and definitely over this. So now we have a map that we can work with, and the next step is to generate the analytic signal map, which suppress some of the original magnetic field and highlight only the near surface targets, the ones that stand out. To do that, open the same surface plot dialog and simply select the analytic signal tab. Leave the scale limits off for now at default, but enable the shading. Make sure we still have the same line bias attached and the base station correction enabled, and click add. So this process generates a total field map with those settings first and then converts it to the analytic signal map. So that's our analytic signal map. It looks like the color scale needs to be adjusted because Bob will automatically assign the highest color to the highest peak on the survey, which is this anomaly here. So this value here is considered red, but what we want to do is assign a lower value so that other anomalies also show up on this color scale. The rule of thumb for selecting the color scale values is to basically look where the green to yellow transition is and maybe reassign that to the peak of the map and see how that works. So you can do that here. So the transition from yellow to red happens approximately around 125. So we can set this to 125 and see how that improves the picture. Each survey is unique in the magnitude of anomalies that it captures because it has to do with the altitude of the vehicle and there's line spacing. So the color scale can be adjusted depending on which aspects of the survey data you wish to highlight and which aspects you want to suppress. Clearly, most of the anomalies with the scale set to 120 still don't show up, so we can further decrease that to maybe 60 and see how that improves the data. With experience of processing data, you will probably settle on a particular range that seems to work for particular altitudes. In this case, some value such as 30 would probably be more appropriate, but we can arrive at that value by increasingly adjusting the maximum limit. So this time we can try 30. That's approximately close to the yellow color here. This is much better. than the original map that we started with. It's the same data. It's just presented differently by adjusting the color scale, making all the anomalies that we want to see pop a lot more readily than here. What we also see is there's a little bit of low-level noise that creeps in between the anomalies, and that can be resolved by increasing the lower limit of the color scale. So far we've been decreasing the upper limit, but we can also increase the lower limit. And usually you can do this by setting the lowest value to approximately where the blue to cyan transition occurs, something around 3 to 4 in this case. So we can regenerate the map, and let's say set the lowest value to 4 nanoteslas per meter and the peak value to 30. Unfortunately, you cannot alter the color scale values once the map is done. You have to do it during the map making process. So this is a terrific improvement compared to what we started with, right? All the same information, it just represented a little bit differently. Now what we can do is delete the maps that we don't need and keep only the ones that seem to work really well. So now we have our original analytic signal map, and then the final fine-tuned result that shows the anomalies really well. So now somebody can go and pick these anomalies on the survey lines and then give them names. So for example, if this there's a number of numbering conventions. But we can give the anomalies names based on the line on which they occur. So if this one occurs on line number 43, let's just double check. Yeah, 43. And it's the first prominent anomaly, or maybe the second prominent anomaly in line number 43. So you can go ahead and select it and open the analysis tool, which, by the way, shows you the key statistics of all the measured parameters in that stretch of survey data. So for instance, the peak-to-peak size of this anomaly is 122 nanotesla. The base value during that interval changed only by 0.4. This anomaly was seen at an average altitude of 2.6 meters. So we can use these two values, 2.6 meter altitude and 122 nanotesla anomaly, to get a very rough ballpark estimate of how big this object may have been, because we know its distance, approximate distance from the sensor and magnetic anomaly. So here we have line 43, target 2. And that adds a target icon to that particular target. Then somebody can methodically go through all of the most prominent anomalies and assign names to them. Using the Alt and mouse, you can zoom in on a particular anomaly and then select it with more precision. Make sure your cursor is on the center of the anomaly on the analytic signal map. Not on the profile, but on the map. Open analysis and then give it a name. So this one occurs on line number 35. Let's target, let's say number 2. So this one is 292 nanoteslas and was measured at an altitude of about 2.6 meters. We continue this process until everything is done. But in general, this concludes the processing part. We have imported the data. We have imported the base station correction. We have created the first total field map that revealed that the data requires heading bias correction. We then determined that the heading bias value of 7 nanotesla needs to be applied to every single line. And then that revealed that some of the lines are still out of alignment with the rest or off the level. And then applying the base station correction fixed the total field map completely. Then we transitioned to the analytic signal map and then customized its color scale so that all the important anomalies show up and the base level noise is suppressed. So essentially, this is the total field map of the area, and this is the gradient or slope map. The total field map shows all the slopes and so-called magnetic field hills, as you may have, plus the tiny anomalies that occur on those slopes. The gradient map eliminates the slopes, highlighting only the sharp anomalies that represent near-surface targets. The final step here would be to save this map. Export map, and you can export it to a particular folder if you as a GeoTIFF or PNG or JPEG. The GeoTIFF will make a georeference map that you can then bring in here as a background map. The one step that I did not illustrate was adding a background image to the map. If you have a georeferenced navigational chart or satellite map, you may be able to add it here. It just has to be in a GeoTIFF format, georeferenced to UTM and WGS84. Otherwise, it will not be imported by Bob. So here we can see where our survey occurs, what depth it was in, and where it is in relation to the shore. When saving the map, Bob will save it using the what you see is what you get principle. So any map elements that you have enabled here will make it into the final map. You can save a backup copy of this processed survey to an MMS file, or you can select particular columns of data and export it to a CSV file. This is the selection of columns you want to export, and it gives you an option of which coordinates to use, whether you want to export the data only within the survey lines or the entire thing, whether you want the base station and the heading bias corrections applied here, and which of the available data parameters you want to save. That data can later be imported in other third-party processing software, or perhaps for integration with other previous year surveys in the same area. And this concludes the data processing for the AUV magnetometer data. Thank you.